Welcome, everyone. Thank you all for coming. I've really been looking forward to give this talk, so I'm happy that so many of you actually made it here. Welcome in. If you want to stand up, there's room in the back, but I'm afraid we're actually out of chairs. There are 2 chairs there, and you can probably take them and pull them down there if you want to. So my name is Mark Seemann, and if you want to know more about me, there's you can go to blog.plur.dk. There's an About Me page there, and you can read all about me. So I'm not going to spend your time with that. I'm on Twitter @Plur. And as you can tell, this talk has the title From Dependency Injection to Dependency Rejection. So like 5-6 years ago, I wrote a book called Dependency Injection in .NET. It was published in 2011. And since there is this word rejection in the title of this talk, you may be expecting that this is going to be some sort of talk where I finally realize the errors of my ways and do, repentance here and retract everything I wrote in a 500 pages book there. It's not going to happen. I'm actually pretty happy with the book. I think it was a good book for the topic. Surely there were things that I would change today, but overall I'm pretty happy with this book. And I think it talks about dependency injection, and I think if you are doing object-oriented programming in C# or even in Java or something like that, dependency injection is a well-known, well-understood, and well-described way to deal with issues of coupling and code maintainability and so on. So I'm not really going to retract any of those things. But also, since basically that time frame, I've become increasingly interested in functional programming. I started with F#, and I'm also now looking into Haskell and other programming, functional programming languages. So sometimes people ask me, in functional programming, how do you do dependency injection in functional programming? So that's actually what this talk is trying to describe and trying to answer that particular question. So there's going to be some back and forth, and I'm going to tell you what other people tell you, and then I'm going to tell you that may not always apply. So I think it's safest to actually start with the conclusion up front so that there will be no confusion. So just to reiterate, if you're doing object-oriented code, dependency injection is still a perfectly valid way to deal with coupling and maintainability issues. If you're doing functional programming, if you're working with a non-strict functional programming language, like for example F# that enables you to do impure stuff just mixed in with pure stuff as well, lots of people will tell you that the appropriate approach to dependency injection in languages like that is something called partial function application. And I'll tell you what that is when I get there. So if you've never heard about that before, don't worry, I'll cover that as well. And it turns out that it's true. These 2 things are almost exactly equivalent to each other. It also turns out, though, that it's actually not a functional thing to do. So just to be absolutely clear, I'm not saying partial application is not functional, but using partial application to do dependency injection turns out not to be functional. So I'll tell you why that is as well. And then since I tell you that that's not functional, I'll also need to tell you, so what is the functional way? And it's basically just a way to compose functions so that you keep the pure and the impure stuff decoupled and still talking to each other, though. And so I'll show you how to do that as well. So that's basically the agenda for the next 55 minutes. I think it's reasonable just to start to think about, before we get into the functional stuff, just do a brief review of, what does it actually mean, dependency injection in object-oriented code. So Rune Bjarnesen gave a talk at a Scala conference a couple of years ago. He says, well, dependency injection is really just a pretentious way to taking an argument. And there's actually quite a bit of truth to that, but I want to talk about, why on a certain level he's absolutely correct, and then also on another level it's a little bit more involved, and then you can write a 500 pages book about how it's more involved. But I'm not going to do that here. It's pretty simple stuff actually, but we need to modify that statement a little bit. So I'll show you that first, just to do a review of what do I mean when I talk about dependency injection, and then we'll look at how to do this in functional programming instead. So in order to do that, I think it's important to start with an example so we have some code to look at. So I'll look at the same scenario all the way through, but I'll write it in different languages and different styles. So the scenario is my favorite scenario, which is suppose you are being asked to develop an online restaurant reservation system. And I know these things already exist, but just bear with me for the sake of the example and imagine that you have to develop yet another one of those. And you know what they work like. You go into an app or website or whatever, and you pick a restaurant and you pick a date, and you fill in a form with your information, and then you press the submit button, and what's going to happen then is that the application is going to post a JSON document to some HTTP-based web service somewhere, and your specific task right now, or our specific task you could imagine, is to develop a HTTP-based web service that accepts one of those JSON documents and handles this request for a new reservation. So just to keep the example simple, we'll go through 5 steps. So the first thing we'll need to do is we need to validate the incoming document because it's JSON, it might be malformed. But if we understand what the JSON document says, we can now we understand which time slot it's asking about. So now we can go and query our database of existing reservations to figure out, how many reservations do we actually have for that particular time slot. And once we have that information, we can make a decision. Do we accept the reservation or do we reject it? If we accept it, we'll save it into the database. Otherwise, we'll not do that. And then, we'll return a response, an HTTP response back to the caller. And we might shortcut in various ways here. For example, if validation fails, we'll just return a response right away and not do the other things. And also, if we decide to reject the reservation, there's no need to save the reservation if we reject it, but we'll still need to create an HTTP response. So that's basically what I want to do here. So I'll start with a little review of what would that look like in object-oriented code, and I'll use C# for my example, but I suppose the Java would be sort of similar to this. So this example will sort of teach us a little bit about why does dependency injection look the way that it does, and why is it not just taking an argument, but it's taking an argument in a very specific way. So I'll start, since this is object-oriented, C# code, I'll start with a class, and using a framework here called ASP.NET Web API. And if you have never seen that before, that's not, don't worry about that. It's not really important for this talk. You can just imagine that it's some web framework, and that's basically all you need to know. So the first thing I'm going to do here is I'm going to create a method called post. And post takes something called reservation request DTO. So DTO is a data transfer object, just like in Martin Fowler's patterns of enterprise application architecture. And it's just the C# view on this JSON document. So it's just a representation of the data that's coming in as JSON. It's just turned into an object instead. Right. So the first thing we want to do is we want to validate the input. So if you do this the object-oriented way, maybe you have some sort of validator object, and you can call validator.validate, and then it'll return a message. And in this case, the design is such that if the validation message is anything but empty, we consider that to be a validation failure, and we'll just return 400 bad request. And you'll notice that there's a validator object there that I'm calling, and you wonder, where does that object come from? And this is what we need to figure out. Okay, where does that object actually come from? And we'll figure that out in a moment. I'll just talk you through the rest of the implementation. It's pretty straightforward. Now, if you're into domain-driven design, the next thing you might want to say is, now that I know it's valid, I'll map the DTO into my domain object. And I was a little bit lazy there, so I just called it R. But R stands for reservation. So that's my reservation domain model, if you will. And if you're really into domain-driven design, you may want to use this ubiquitous language where you're talking the same language as your domain experts. And in the restaurant business, if you go into a real restaurant and ask if they have a table for 4 people, you'll be interacting with a person called the maitre d', at least in more fancy restaurants. That was the American pronunciation of a French word, so I apologize to the French people in here. So you could have a maitre d' object, and you could ask it whether it can accept the reservation. And in this design here, what we basically do is we get an ID back, so that's the ID of the newly created reservation. But if that's null, we'll return 403 forbidden. So there are various issues with this design, like it violates command query separation, and it uses nulls for real values, which is not a nice thing to do. But lots of people do this in C#, so I thought I'd just keep the example realistic there. But otherwise, if we get past that point as well, we can just return 200 OK. So what we have here is we have 3 dependencies. We have a validator, we have a mapper, and we have a maitre d', which are 3 dependencies. So now we're wondering, where do these 3 dependencies come from, can we make the method post there? Can't we just make the post method takes those 3 dependencies as arguments to the post method? And unfortunately, it turns out not to be possible because the post method is being called. This is being called by convention by our web framework. And most web frameworks are perfectly happy to pull data out of URLs. So in this case, the URL is just /reservations. But if it had been like /reservations /123, and the 123 would have been some sort of ID, web framework would be perfectly happy to pull that information out of the URL as well. And it's also perfectly happy to give me the data that was actually a part of the body of the HTTP request there. But apart from that, you can't really have any other values or arguments that go into this sort of method call there, because otherwise, the web framework wouldn't know how to wire those things up. So we'll need to figure out another way to pass those dependencies in as arguments, and we can't pass them as arguments to the post method, so we'll need to pass them as arguments to the constructor, because where else would we do that? So this is basically dependency injection in a nutshell. This is called constructor injection, and it's pretty well described. And it's not difficult to follow at all. It's fairly straightforward. But then you might say, but this is a special case because this is where your code is interfacing with the framework, and there are rules that the framework enforces, or restrictions. So surely if we go a level deeper and look at just the maitre d object, for example, now here we can control what the methods look like. So surely we can just pass dependencies as arguments, or can we? So I'll start with the try accept method here, and you'll notice that it's a method that just takes reservation as input and returns a nullable int as output. So the sort of the contract here is that it returns the ID of the reservation if that reservation was saved into the database, and if it returns null, it means that we couldn't accept the reservation. So the way we might implement this is we'll say something like we'll call a reservation repository, read the reservations for that particular date, and do a sum over all the quantities. And that gives me a number of reserved seats for that particular time slot. And then I can make a decision, and that's pretty straightforward. I can say, well, if the number of already reserved seats plus the reservation quantity, if that's less than or equal to some capacity, which is another number, I can accept the reservation, and I can call reservations repository create, and that creates a new row in the database, and it returns the ID of that new row, and I can return that ID. And otherwise, I'll just return null, something like that. So you might say, well, all right, so I have at least one dependency there, a reservations repository. Can I just make try accept take that as an argument? And it turns out, unfortunately, I can't, because maitre d implements this interface called imaitre d, and it defines try accept to have this particular shape. So I can't just go willy-nilly and add more arguments to that method, because then it wouldn't compile. And then you can say, well, but couldn't you just add those extra arguments to the interface as well? And that would be a leaky abstraction, because it's an implementation detail that this particular implementation talks to a reservation repository, and I could have implemented this in a lot of other ways. Maybe I want to add a decorator that does logging, or I want to add a decorator that does caching. So if I want to do caching, for example, maybe I want to have a caching object that I read and write to. So should I pass that as an argument to the function, to the method as well? So it's sort of like, if I did it like that, the argument list would just grow and grow, and I'd be violating the dependency inversion principle, I'd be violating the open-close principle, and a lot of other things. So I sort of need to be able to say, this is the abstraction. I take a reservation, I want to get an ID back if the reservation was accepted. That's the abstraction, and all the other stuff is just an implementation detail. So again, I just need to do constructor injection because that's the only thing I can really do. So it sort of goes like that all the way through, and it's a pretty consistent pattern, and you can apply it over and over again, and that's basically how dependency injection works. So that's just a little bit of review of what does it usually look like in object-oriented code. And before I continue on, I just want you to remember a couple of things, because I'm going to rewrite this code in different languages now. So this is a class called maitre d, and it has first of all, it has a primitive dependency on a capacity. So you'll see capacity is just an integer. It's just the number of people who can eat at the restaurant at the same time. And then I have this reservations repository. But if we break down the interaction with the repository, you'll notice that I call two methods on that repository. I call read reservations to get the reservations for a particular date, and I call create in order to create a new row in the database. So this repository may have lots of other methods as well. We don't really know. I'm only using those two methods. So in practice, I'm sort of conceptually, I have three dependencies: the capacity and those two methods. That's basically what I have to deal with here. Right. So that's a review of what it normally looks like in object-oriented programming, and this is what you can read all about in the book that I wrote and so on. So I don't really have any particular problems with that if you're doing object-oriented code. So how do you do dependency injection in functional programming? This comic talks about Scala, but it could be anything. You don't, because Scala is a functional language. Fine, it's functional. How do I inject in dependencies? You write a free monad, which allows you to build a monad over from any functor. Did you just ask me to go fuck myself? I believe I did, Bob. Yeah. You will find functional programmers who will actually give you that answer, that you have to use a free monad in order to do dependency injection in functional programming. And it's not wrong. You absolutely can do that. But when we get into monads, and particularly free monads, things become complicated quite fast. So fortunately, in most cases I've found in practice, there's a much simpler, much more straightforward solution than using a free monad. So I'm not going to talk about free monads at all, although it is a thing you can do. I'm going to tell you how to do things in a much more, much less complicated way. So if you ask a lot of people who are already, experts in F#, for example, so if you ask them, how do I do dependency injection in F#, they'll tell you to use something called partial function application. And as we'll see, I sort of told you this already at the beginning, this is a perfectly, it's almost a perfect analogy to dependency injection in C#. There's a very near correspondence between those two, but it also turns out not really to be functional. But it works, and it does what you want it to do, so if you can live with it not being functional, it's a perfectly valid thing to do. So I'll show you what that looks like first, and then I'll show you why it's not functional, and then I'll show you, what to do instead. So now we'll shift, move away from C#, and I'll start writing some F# instead. I'm not assuming that you can read F# already, so I'm sort of walk you through the important parts of this. So here's the beginning of a function. This doesn't compile at the moment because I haven't actually written the function. I've just sort of written the declaration of it. So let's just stop here and talk about it. So you'll see that there are 3 lines of code here. The top ones, the green ones, are just comments. So the only line of code that we actually have is the one that starts with let, and it has all white letters for the rest of it. So try accept is the name of the function. And then there are 4 other words: capacity, read reservations, create reservation, and reservation. Those are arguments to the function. So this is a function that takes 4 arguments, which is a bit at the high end, I think, but maybe we can live with that. And then I've tried in the comments to describe what are the types of all of these things. And the way that F# works, that once you've actually written your implementation, then the compiler infers what the types are. So at the moment, the compiler, since this doesn't compile, it doesn't really make sense to talk about the type of the function as it is at the moment. But this is the type of the function as it will be once I've written all the code. So the way that we read this is you can tell on the first line there, it says int after the 2 slashes. And that's the type of the capacity argument, because you just read it by position. So capacity is just an integer, and it corresponds to that capacity that I injected into the maitre d object before, if you remember the C# example. Now the next thing I have there is brackets begin, datetime offset, arrow, reservation list, bracket end. The reason why it's in brackets is because it's a function. So this is one argument, but the argument is a function. It's a function that takes a datetime offset as input and returns a reservation list as output. And the same goes for the other bracketed one that says reservation to int. That's also a function. Now these 2 functions together play the same role as the repository in that maitre d example that I showed you before. I just, instead of defining an interface, I just broke them out into 2 functions, because it's a more lightweight way of approaching the problem. You don't have to declare a new type. I can just say these are 2 functions. And then the last argument, the last input argument, is the reservation. We're trying to figure out whether we can accept that or not. And then on the next line, you can see the return type of this function is going to be int option, which is sort of you can think of it as the same as a nullable int, but just options in F# is a much more sane approach to model, values that may or may not be there, because they're actually type safe, whereas null is not. Null doesn't have a type. It's a way to stay sane and still think about values that may or may not be present. Right, okay, so the implementation is pretty straightforward. It basically follows the same steps as you saw in C#. First, we'll try to figure out what's the number of already reserved seats. So we do that by calling the function that was passed in as an argument with the reservation date, and then we do a sum over the quantities. Now, if you've never seen this vertical bar and the greater than sign before, it's a pipe. It works just like pipes work in Bash or in PowerShell, so if you've ever done scripting like that, it's basically the same thing. It means take the value on the left-hand side of the pipe and use that as an input value on the right-hand side of the pipe. So in this case, I'm calling read reservation with the reservation date. That returns a reservation list, and then I use the reservation list as input argument into list.SumBy. That's basically what it means. And you'll see this over and over and over again in F#. This is something, it's basically the symbol of F#, almost. So that gives me reserved seats. That's an integer. Now I can make the same decision as I did in C#, where I just say, well, if the reserved seats plus the reservation quantity, if that's less than or equal to the capacity, I can accept it. So I'll just set is accepted to true, and I call create reservation, which is the other function argument. And that returns an integer, and I just pipe the integer into sum, which is one of the cases that options can have. If I decide not to accept the reservation, I just return none. So that's an int option. And that's really all there is to it. And then you may say, well, but that's not really equivalent to the maitre d object, because how do we implement, or how do we tell, if we have a real application, how do we actually connect that with a real, some code that actually talks to a real database? So let's try to look at what that looks like. So if you remember the interface, the maitre d interface that I showed you before, defined a method called try_accept that takes a reservation as input, returns a nullable int as output. So I'm aiming for the same shape of abstraction here. I want to take a reservation as input, return an int option as output. So what I want to do here is I write a new function called try_accept composition, because it's just a function that composes the other stuff. So first, I need a read function. So if you imagine that I have a DB module that contains real code that connects to my SQL Server or Oracle or whatever that might be, that's actually a function. And this function takes a connection string as input. It takes a datetime offset as input. It queries into the database identified by the connection string. It queries my reservations table for that, all the reservations in that datetime offset, and returns all the reservations that are in the table there. So you'll notice that this is a function that takes two arguments and returns a reservation list. Now what I can do is I can call this function with one of the arguments. I can call it with the connection string, and the return value of that is another function that is waiting for the remaining arguments. This is function application. This is partial application. This is all partial application is. You just, instead of this is not really possible to do in C#, but here you can do this. You just call it with some of the arguments, and you just get a new function back that's waiting for the arguments you didn't supply. So that's another function. And this function has the shape that we want it to have. And you can do the same thing with the create function. You can say you can partially apply db.create reservation, and you get a function that takes reservation and returns the ID of the new row that it created. And it actually talks to a real database. And now you have all the information, or almost. If you hard-code the capacity, you have all the information you need, and you can call try_accept. So I just hard-coded the capacity of the restaurant to be 10, because 10 is an easy number to think about. This would obviously mean that it's a very small and intimate restaurant, but that's besides the point. So this is a call to try_accept with all four arguments passed in. And this is the last expression in my function, and that just means that becomes the return value of the function. So try_accept returns an int option, which means that this function also returns an int option. So that's basically how I can compose those things together. Now, one of the things we might notice, though, is that try_accept composition, this function takes a reservation as input, and it passes the reservation as the last argument to try_accept. Now, if we have that situation where we have the same value or the same argument on both sides of the equal sign, and they're both in the last position, we can perform something called an eta reduction, which means we can remove them. This is just almost like when you do equations in mathematics, you can also sometimes, cancel things out if they appear on both sides of the equal sign. So now it looks like the tricomposition is not really a function anymore. It looks like it's a value. But if you look at what the value is, it's a partially applied function because it's the function call into try-except with only 3 of the 4 arguments that try-except needs. So the return value of that is a function that is still waiting for you to supply the reservation. So this is exactly equivalent to what you saw before. Now the reason why it's interesting to perform an eta reduction in this case is because F# is a .NET language, and it means that it compiles to IL, which is the intermediate language or the intermediate language that .NET uses. And what you can do with the IL is you can decompile it into C# if you want to understand what's going on. So if you do that, you get something back that pretty much looks like this. I had to clean it up a little bit because it came back with lots of attributes also. But basically what you get back is something like this. You'll notice it's a class. The class has a weird name. It's actually not valid. It's not a valid C# name, but it is a valid IL name. So this actually works. It's a class. The class has class fields that corresponds to the capacity and the create reservation on the read reservation functions. The class has a constructor that takes those 3 arguments and assigns them to the fields. And then it has an invoke method down there in the bottom that composes all of those things together. It's constructor injection. Partial application is the same as dependency injection. In .NET, it even sort of compiles to the same sort of code. So the people who tell you that in order to do dependency injection in F#, you just use partial application are absolutely correct because it is the same thing. Now, the only thing that remains to investigate then is it functional? So you might stop right here and just say, well, I don't really care about that. I just want it to work. And this works. So you can absolutely go and just keep it at that and then start using F# and do dependency injection with partial application, and all will be, in general, as good as it was in C# with dependency injection. So that's fine. But if you're really interested sometimes in learning, whether it's really functional, because if you want to learn, what does it actually mean to write functional code, you might be interested in investigating whether this is the case or not. So in order to answer this question, first and foremost, we'll need to establish, what do we mean by something being functional? And it's sort of like when you ask people about, please give me a definition of unit testing, you'll get all sorts of different answers, and some people will always find someone who, violently disagree with what most people agree on. So you can't really get any sort of consensus. And I think it's a little bit the same with functional programming. You can't really get, everyone to agree on a common definition of functional programming. But I think a pretty mainstream one is that functional programming must have an emphasis on something we call pure functions, because pure functions have lots of good qualities that we like them for. They are easily composable, they're easy to reason about, they're easy to unit test, actually, and lots of other things. So first of all, we need to talk about, okay, what does it mean that a function is a pure function? And it means it has to have 2 qualities, or 2 properties. The first of these properties is that it must return the same value for the same input. In other words, it must be deterministic. And if you've ever looked at, all of you know basic math. So you know that, 2 plus 2 is always 4. It's deterministic. And 2 plus 3 is always 5, and so on. Mathematics tend to be deterministic. But it doesn't have to be constrained to mathematics. If you want to reverse a string, if you take the string foo and reverse it, you always get oof back. It would be strange if sometimes, something else happened. That's a deterministic operation as well. But just to be absolutely clear, when we're talking about functions being deterministic, we're talking about that they always return the same input, or the same output for the same input. So if you imagine, for example, that you have a function where you give it a file name, and then you ask it to read the contents of a text file and turn it into uppercase, for example. That function wouldn't be pure, because even you'd say, well, it's deterministic because I know what's in the file. But you could change the contents of the file name between 2 function calls, and then the output would be different. So we consider files to be external to the function, so such an operation is not considered to be pure. Also, if you read from a database, that is not considered to be pure because it's non-deterministic for the same reason. The other quality that a pure function must have is that it must have no side effects. Side effects are all sorts of things that happen, as a side effect. So, if you call a function and it sends an email, sending an email is a side effect. If you call a function and it writes into a database, that's a side effect. If it deletes a file, that's a side effect. If it puts a pixel on your screen, that is a side effect. So basically what we covered now is that all the things you'd ever want to do in order to have a valuable piece of software is impure. You want to read and write for databases? That's impure. You want to put things on the screen? That's impure. You want to send emails? That's impure. Basically all the reasons why you would ever develop software, you can't do that with pure functions. Pure functions in themselves are utterly useless. And it's one of the reasons why sometimes functional programmers have this tendency to be regarded as, ivory tower astronauts that really have no connection to the real world. But, functional programmers are not stupid. We absolutely understand. Oh, did you notice how I said we, and with the functional programmers, sort of including myself in people who are not stupid? Well, anyway. We absolutely understand that we need impure stuff to happen as well, because we want to be able to put pixels on a screen and send emails and all that stuff. So we do realize that we need to have impure functions. So basically, the design ethos of functional programming, if you will, is that we say we want to maximize the amount of pure code that we have in our code bases, and we want to minimize the amount of impure code that we have in our code bases. And if we do that, we are probably doing something that is functional. So that's basically the design ideal. Now, there's a couple of rules that relate to how those two groups of functions relate to each other. If you have a pure function and you want to call another pure function from that pure function, that's possible because one function being deterministic and having no side effects, it's okay to call that if you want to be deterministic and have no side effects for yourself. Also, if you're an impure function, you can call another impure function because there are no rules for impure functions, and that means you can do everything you want, including also calling pure functions. So you can call pure functions from impure functions. That's not a problem at all. But you cannot go the other way. You can't call an impure function from a pure function. Because if you did, just hypothetically, if you could, that would make your pure function impure, because either you would have invoked a side effect, or you would have introduced non-determinism into your pure function. So that's not possible. So that's sort of the rule. So basically, if you really want to, just have a high-level idea whether the software that you're writing, whether it's functional or not, you have to ask yourself the question: does my code adhere to that rule that you can't call impure functions from pure functions? So people sometimes ask me, how do I know that I write functional F#? F# is this multi-paradigmatic language where you can write functional code, but you can also write object-oriented code, and you can do all sorts of impure stuff. And basically, unfortunately, in this case, the answer is you don't really know whether you're writing functional F# or not, because F# is such a friendly language that it'll allow you to do lots of things. It tries not to get in your way. It tries not to be restrictive, but it also means that it doesn't really tell you whether what you're doing is actually functional or if it isn't functional. So sometimes, in order to figure out how to answer this question, I need to do a little bit of a sanity check, and I need to have some sort of tool that can tell me whether or not my design is actually functional or not. And F#, unfortunately, cannot really answer that question. But Haskell can. Haskell actually enforces that rule. And fortunately, F# and Haskell are languages that are similar enough so that if you avoid the object-oriented parts of F# and actually try to write something in F# that is functional, it's fairly easy to port your F# code to Haskell. So we can try to do that here. So here's the try accept function ported to Haskell. And I'm not going to walk you through the implementation body of the function itself, but if you just look at the top 2 lines, that's the type of the function. And you'll see it looks a lot like what we already saw before. It's just that datetime offset is now called zone time, and a reservation list is not called reservation space list. It's just called reservation with square brackets around it, and that means it's a list. And it's not called an int option. It's called a maybe int. But apart from that, it's basically the same thing. Maybes are exactly the same thing as options. This compiles and does whatever we think it should do. So far, so good. That's actually not so much a problem. But one of the things we need to realize about this function is that this function is pure. How do we know that? Well, we know that because all functions in Haskell are pure by default, unless explicitly declared to be impure. And this one is not explicitly declared to be impure. I'll show you what that looks like in a moment. So this function is pure. Not only is it pure, but the two function arguments there are also pure for the same reason, that they are not explicitly declared to be impure. So those two functions are pure. And this is the only thing they could be, because if they were impure, remember, we couldn't call them from a pure function, because you can't call an impure function from a pure function. So they have to be pure, because otherwise this wouldn't compile. So fortunately, they are pure. All right, fair enough. So how do we compose this with something that actually talks to a database? Now, as I already covered, talking to a database is impure. It's either non-deterministic or has side effects and may even do both things at the same time. So if we want to compose these things together, we realize that that's going to be one of those impure functions that we know that we need to have. So that's fair enough. So let's declare our composition of these things to be impure. So that looks like this. Try except composition is a function that takes a reservation as input, and it returns IO of maybe of int as output. And that type IO there, that's the way that you explicitly declare that a function is impure in Haskell. And there's a lot of theory that goes around that, and I'm not going to bore you with those details. Just accept that this means it's impure. All right. So if we want to do the same thing as we did in F#, I'll first define read to be the partially applied db.read reservations with a connection string. The type of that is zone time to IO of list of reservations. IO because it's impure. Likewise, create is also the partially applied db create reservation function, and the value of that, or the type of that, is reservation to IO of int. Again, IO because it's impure. It returns the ID of the newly created row in the database, but it's impure because it was a side effect. So we can try to call try except with all the arguments just like we had before, and we can do something like this. Try except 10 read create reservations. But if you recall, and you probably don't, so I'll help you here, read ought to have the type zone time to reservation list. Create had to have the type reservation to int. These types are not the same. A reservation list is not the same as an IO reservation list. These are different types. And you can't really reconcile those two things. This doesn't compile. It doesn't compile exactly for the reason that I told you, that you can't pass an impure function to a pure function, because that would make it impure as well. And Haskell enforces that rule. So it's not functional. Yes, partial application is exactly the same thing as dependency injection when used with dependencies, but it's not functional. Again, I have to stress that I'm not saying partial application in general is not functional, but used for dependency injection, it works in F# and all, but it's not functional. You can't make this you can't make this compile in Haskell. So let's try to understand why that is at a more intuitive level. If you're looking at dependency injection, what you often end up with is a graph of objects, and the graph is always a directed acyclic graph. So in this case, what I'm trying to picture here is that you have a root object that has two dependencies. So the root object is the object on the left-hand side, and then it has two dependencies, and then the top one of those has two dependencies, and the bottom one only has one dependency, and so forth, until you have a graph with leaf nodes. Now, the leaf nodes are typically where you have all your impure stuff happening. These are the dependencies that actually talk to databases and send out emails and all sorts of things. And they are almost by definition impure. So if you have something that is impure, and you have another object that contains and calls into the impure code, that means that caller must also be impure as well. So impurity is totally infectious. Dependency injection makes everything impure, and that's why it's not functional. Okay. So if we want to be functional, we have to reject the notion of dependencies and sort of find a different way to deal with the fact that we have impure stuff happening, and we sort of want to decouple the impure and the pure stuff that's happening in a sane way, but we can't really do it with the way that we're used to do in object-oriented programming. So what do we do instead? So I'll walk you through that as well. Right. Okay, so in order to understand what to do, let's go back to basic stuff. So back when you learned how to program, the first thing you probably learned was to do some sort of hello world or something like that. And fairly early on into your programming 101 or whichever way you learned to program, you probably learned that it's a good idea to factor common code out into some sort of operation. You know, a procedure, a sub-procedure, a method, a function, whatever you want to call it. We'll just call it a unit of operation. And such units, you know, operations, procedures, functions, methods, they take input in the form of an argument list, and they return output in the form of return values. So that's input and output. Everyone knows that procedures or units have input and output. But if you start to look at, you know, dependency injection and object-oriented design, you have dependencies. And you want to have data in and out of those dependencies as well. So if you think about the maitre d object that I showed you, up until now, you know, the maitre d queries its repository or queries its function argument to get data from a database, and in order to make some decisions based on that data. That's also input, but we call it indirect input because it's not part of your argument list, but it's still input into the unit. And also, if you want to put data out into your dependencies, if you want to save the reservation, for example, that's indirect output. So now you have direct input and output, and you have indirect input and output. And basically, the problem is that we've now learned that dependencies tend to be impure, so we want to get rid of those. So we need to figure out a way to get rid of indirect input and output. So let's start with indirect output. Now, why do we do indirect output in C# or Java or things like that? Well, why don't we just return the indirect output as normal output? Couldn't we do that? And the reason why people tend not to do that is because often that indirect output must not always be, put out, if you will, must not always be returned. It's conditional on some sort of condition. For example, in the try accept example that we've seen here, the indirect output is that we save the reservation into the database. But we only want to save the reservation into the database if we decided that we had enough capacity in order to accept the reservation. And otherwise, we don't want to do that. And it's difficult in C# and Java to decouple the decision from the effect because these languages are statement-based. So you have if-then statements, and then you have more statements that sort of, achieve some sort of effect, like saving into a database. So I'm not saying it's impossible, but it requires a fairly sophisticated object-oriented developer to decouple decisions from effects in C# or in Java. It can be done, but it's sort of not the easiest thing in the world. So most people just resort to this thing where they say, well, if I can accept it, then I'm just calling my repository, and otherwise I'm not calling my repository, and then that becomes indirect output. But it turns out that in functional programming languages, decoupling decisions from effects is one of the easiest things you can do. So we can take that indirect output and refactor it to be direct output instead. And in F# it's going to look like this. So this is where we left off before. I have my try accept function there, and it takes 4 arguments. Now the argument that produces direct output, or indirect output, is this argument called create reservation here, which is a function. It's a function that takes reservation as input, and that's actually the direct output. And then it returns int, and then we take that int and return that instead. What I want to do now is that I don't want to call this function anymore, so I don't even want to pass in this function as an argument anymore, which also means I can't return an int anymore because I don't know what the ID is going to be. I just want to return my decision, and then some other function that composes these things together can make the decision of, for example, writing into the database. So instead of returning an int option, I just want to make the decision as returning a reservation option like that by removing that function argument all by itself and just do this instead. So I've removed an argument, so this is now a function that only takes 3 arguments. And that also means I can move things around because it can fit on one line now. So the implementation of this needs to change a little bit as well. I start by basically doing the same thing, getting the number of reserved seats from my read reservations argument function there, and then all sorts of other things. But when I decide to accept the reservation, instead of calling a function, which is no longer there, I just take reservation, set is accepted to true, and then pipe that into sum, and that becomes a sum reservation. And if I decide not to accept the reservation, I just return none. So I've pretty, clearly encoded my decision in the return value, and then, someone else, a caller, can decide what to do with that decision. So if we look at the try-accept composition that we saw before, I'll need to refactor this one as well. So you'll notice that the type is still the same. So this is a true refactoring. I'm not changing the behavior. I'm also not changing the API. These things stay the same, but I'm changing the implementation. So what I need to do now is I need to call try-accept with the 3 arguments that it now takes and get the value back from that. So I call it with the argument, the hard-coded argument 10, with the partially applied function db read reservations with the connection string, and with the reservation. That's all the 3 arguments that it takes now, and it returns a reservation option. And you'll notice that I've surrounded that function call with match with. And that means I can now do pattern matching on the return value of calling that function. And if it's none, I'm just going to return none. If it's sum, I can pull the reservation that was accepted out of the sum case, and then I can pass it as an argument to db create reservation. And that is a function that creates the reservation as a record in the database, returns the ID, the row ID of the new row that was created, and then I can take that ID, that integer, and pass into a sum case. So that is why this function still returns an int option. This behaves just like the previous example that you saw, but now I've refactored it to not have direct output anymore, or indirect output. It's only direct output. So I've decoupled the decision from the effect, which is an easy thing to do in F#, and it's also easy to do in Haskell for the same reason. And this sort of branching here is such a common thing to do on an option that it's built into the language or built into the F# library. It's just called option map. So this does exactly, the option map is just saying, well, we always map none to none, and then we take a function that in the sum case we can invoke that function. So this is exactly the same as before. And you'll notice now that I have R sitting there on both sides of that arrow, and that arrow inside this lambda expression has the same role as an equal sign in a lit-bound function. So I can do the same sort of eta reduction as I did before. It's not really important, but it just makes the code a little bit nicer, so it looks like this. And I can also take and move the reservation around. That's also not really important, but I just thought it would look cool to move the things around. Right, okay, so that was a refactoring that got rid of the indirect output. Now, can we also get rid of the indirect input? That's even easier in most cases, because why do we actually need to call a function or call a method from within the unit? Why don't we just say, I need that information, instead of calling a function that returns a reservation list? Why don't we just say, I need a reservation list in order to make the decision. Someone else, fetch that reservation list from wherever you want to and give it to me. So if I do that, I can just say, well, indirect input should be direct input. And you'll notice what happened now. There are no more arrows between the unit and the dependencies. So now we have rejected dependencies as a notion, and this puts us in a position where this unit can actually be pure. It's not quite there yet, but we're really, really close. I just need to make this refactoring, and then it becomes pure. All right. So at the moment where we left it off, it wasn't pure, but I'm going to make it pure by removing the indirect input and moving the indirect input to direct input. So the indirect input is in this remaining function argument there. And I should say, just as a side comment here, I'm not saying that passing function arguments to other functions is not a functional thing to do. It's one of the most functional things you can do, in general in functional programming. But what I'm saying is, when the implied behavior of a function is that it's almost always going to be impure, then it doesn't work because that would make the other function also impure. So in general, I have no problem with function arguments, but in this case, the problem with this one is that it's implied to be impure. So that's why we don't want to have it. So what I'm really interested in that read reservations function is not so much the input, but the output that it creates, that reservation list. So I can get the reservation list if I just change it from being a function to just being a value that's just a reservation list. And if it's a value, I don't need the brackets around it. Also, if it's a value, it doesn't really make sense to call the argument read reservation, so I'll just rename it to reservations like this. All right. So this version of try except now looks like this. I just take the reservations, I do a sum over the quantities, and I do all the stuff that I did before. And this is also now simpler, so that I can actually move things into one line. So it just becomes simpler and simpler the more I move it towards something that is pure, which is one of the reasons why we like pure functions, because they're simple. It's really difficult, actually, to write a complicated pure function. Yeah, well, that's a catchphrase. And it's a lie, but never mind. Just believe me. Right, okay, so we'll go back to try except composition and see if we can refactor that one more time in order to still, keep the API, keep the behavior, but do it in a different way. So what I want to do now is I'll start with the reservation date, and I'll pipe that into db.read reservations. So if you remember, db.read reservations partially applied with a connection string is a function that takes a date as input. And I'm piping the date as input, so that's actually the same as just calling it with as a second argument. Now this returns a reservation list, which is exactly what I need. So I'll pipe that reservation list, which is the output of this expression so far, into a new function. In this case, the function is a lambda expression for now, anyway. So you'll see the lambda expression here is a function that takes reservations, a reservation list as input, which is the output of the previous step. And then I just call try except 10 reservations reservation. That's just a complete call to try except the function that I just refactored, and you know that it returns a reservation option, so I can just do option map just like I showed you before. That hasn't really changed. Now, the first time you see lambda expressions in C# or in which other language you originally saw them, you think lambda expressions are really cool. And then, when you've seen like 1,000 of them, you begin to think that they actually look a little bit awkward. So you're looking for ways to refactor them so that they look nicer for some definition of nice. And in this case, you may be wondering whether we could make it look nicer. So you'll notice that it says reservations on both sides of that arrow. But unfortunately, we can't do an eta reduction in this case at this time, because reservations need to be in the last position on both sides of the arrow in order for us to be able to do an eta reduction. And reservations at the moment is the second to last argument and not the last argument. So I can't really do that. Sometimes when I encounter a problem like that, I just go back to the code that implements the function and just change the order of the arguments there, because often it doesn't really matter. In this case, I think it actually, it makes more sense to think about try except as having this particular order of arguments. So I'm not really interested in going back and changing the function itself. But there's a little trick I can use. Now in Haskell, for example, in the core library of Haskell, there's a function called flip. And it's not in F# core because Don Simon doesn't like it, but I do. And it's super, super easy to implement yourself. It's just one line of code. Here it is, flip. And I'm not going to try to talk you through this because that's typically where people's brains explode. But flip is a function that takes another function as input. And the function that it takes as input is a function that takes 2 arguments. And it returns a new function that does exactly the same things, but with the arguments flipped around. And this is what I need to do. I want to flip the arguments of this. But the only problem that I have is try except is a function that takes 3 arguments, and flip only works for 2 argument functions. That's not a problem either, because I can partially apply try except with the number 10, and if I do that, I'll have a function that takes 2 arguments, and then I can flip them. Okay, so that looks like this. Yay. So now I have reservations on both sides, in the last position in both sides, and then I can do an eta reduction, and that looks much nicer. Yay. This has nothing to do with dependency injection or anything, but I just thought it was cool, and I had the time, so whatever. All right, okay, so does this compile in Haskell? Okay, here's our sanity check, and you can sort of probably sense where this is going, right? It's not going to be particularly surprising, but let's just look at it anyway. So here's the port of try except, and again, I'm not going to cover all the nasty Haskell-y implementation details, but we see that the function is still pure because it doesn't say IO anywhere in the function type. So that's good. Now, what about try except composition, that composition where we try to compose it? Well, it looks like this. And you'll notice that it has all sorts of weird-looking arrows and dollar signs and weird-looking stuff. But you can probably see some things that are a little bit familiar, like, for example, that flip try except 10 there in the middle actually looks like it did in F# as well. But the important message here is that, yay, this actually compiles. It works. This is the functional way to do it. And if we want if we try to extract some sort of pattern out of what happened, I've seen this happening over and over again when I play around with Haskell, is that what happens is that at the boundary of the system, I tend to have some sort of core of pure functions, but then around the pure function, before and after, I have some impure stuff going on. So in this case, I prepare some input data that I pull from various impure sources. And then I pass that data to my pure functions, and my pure functions then return some pure data, and then I do some impure stuff with that data as well. So it almost becomes like a sandwich. I don't know if you know the story about how sandwiches was invented, but there was this nobleman here in England called the Earl of Sandwich, or was it the Duke of Sandwich? It's the Earl of Sandwich, right? Yeah. And he was a notorious gambler. There's probably been more than one Earl of Sandwich, but one of them was a notorious gambler. He was playing cards, and he was playing cards so much that he didn't want to break for lunch or dinner or anything. So he asked his servants whether he could come up with something that he could eat while playing cards without, he wanted to be able to eat it with one hand, and he wanted to be able to eat in such a way that his fingers didn't become too greased so that he could actually still handle the cards. So they came up with this idea of giving him 2 slices of bread with a piece of meat in between, and this is basically, how the sandwich was invented, because it sort of, addressed that problem. And it's sort of the same thing that happens here, just like the good parts of the sandwich is actually the meat in the middle, but it's greasy, so we can't really handle it, so we put, bread around it. It's sort of the same thing that's happening here. The good parts, all your logic, all the business logic or whatever it is that you're trying to do is in pure functions. It's in the middle. But you can't handle it because you can't see the output of it, because seeing the output of a pure function would require you to print pixels to a screen, and that's an impure operation. And you can't put data inside into the pure function because that's I/O. So you need to have some impure stuff around in order to be able to handle the pure stuff. So Haskell code always tends to look like this. And by the way, I have another talk that talks about why this actually turns out to be the ports and adapters architecture all by itself. It's sort of enforced by the Haskell compiler. But if you ask a compiler, if you tell that to a Haskell programmer, did you know that Haskell programs tend to follow the ports and adapters architecture? They'll look at you and say, the what? They've never heard about the ports and adapters architecture because they don't need to have a name for something that the language does by itself. It's just Haskell. Right, okay, so we'll get back to where we started. I'll just reiterate the slide that you've already seen. If you're doing object-oriented programming and you want to address problems of coupling and code that's hard to maintain, dependency injection is a well-known way to do that. There's other ways to do that in object-oriented programming as well, but dependency injection is well-described, well-known, and so on, so that still makes sense. But in functional programming, if you're in an impure functional programming language, like, for example, F#, but it might be, well, I don't know about Clojure. It's not impure, it's non-strict, sorry. If you're in a non-strict functional programming language like F#, for example, you can use partial application, and I showed you why that is actually equivalent to dependency injection. But also, I showed you why it's not functional. So instead, if you really want to be functional, you need to go with this sandwich model instead, where you say impure, pure, impure, and compose functions like that. So with that, I'm pretty much at the end of the talk. I'm also at the end of my time, so I don't really have time for questions. But I'll be happy to talk to any of you who might have questions, either here or out in the hallway or wherever. I'm going to be around today and tomorrow, and if I don't look totally stressed out, you're always welcome to just come and talk to me and ask me questions. There's one question that I predict some of you will have, and that is, can we get the code? You can just stay tuned. I've actually already written 4 articles that uses all of this and sort of, dives into the details of it. I just need to polish them off when I get back from the conference. So if you subscribe to plug.play.dk, or if you just follow me on Twitter, you'll know when it's published, and I'll probably do that late next week. I think I'll start doing that. So you will be able to get all the demo code that I showed you here, or at least the F# and the Haskell versions of it. So with that, I'm out of time, and I hope you enjoyed the talk, and I hope you enjoyed the conference, and that you have a good couple of days here. So thank you all for coming.